What is going on, guys? In this video, we are going to be doing a application overview of a product that is built on AWS. Previously, I did a video on a resource called AWS White Papers that has a whole bunch of these examples of applications that are built on AWS. And a lot of you wanted to just see a walkthrough of some of these different architectures and see all the different services that are at play. So that's what I wanted to do with you here today, to walk you through this application, how it's built, and kind of how it works. Now, keep in mind, like, these are private companies that are for profit, so they're not going to give you all the details here. So there may be some gaps that we need to imagine or visualize in order to kind of put the whole story together. But I'm going to do my best to try and figure that out with you here today. So this is an application that's built by a company called 3Victors, and it is a streaming airline ticket shopping insights based application. You can see here that it's predictive analytics on time series airline shopping data. And I didn't know much about this company, 3Victors, so I decided to just look them up. So let's go over to their website really quick. So it's just 3victors.com, and here is their homepage. So they are a data company, and they make everything possible, apparently. And they offer real-time data analytics made easy. Let's just take a look at their product page really quick to see what they do. So they offer a real-time 360-degree view of consumer demand, airline capacity and pricing, and air bookings. Okay, that's fascinating. So they offer different, or they have different sources of data. So user-initiated search and responses. So search demand, which is when a user types into a quote box. So this is when someone is searching for, I want to go from Toronto to, I don't know, Paris. So they capture that data, I suppose, from the airlines themselves or a third-party broker. They also have historical data on flight schedules. So, and by the way, I didn't know this, but flight schedules are predetermined, often quite a bit in advance. So this data would be known quite a bit prior to the date of the flight. They also have booking and ticketing information. So when people actually purchase tickets or make a booking to go from point A to point B. And then they have some metadata. What is this for? Use and preserve the most relevant data that you need. Okay, I don't know what that is, but I guess they have some more data that they append to this information to make it more useful. Okay, so they have all this data that's feeding into this pipeline here where they normalize it, segment it, debottle it, aggregate it, and perform some time series analysis, I guess. Then they run some algorithms on it with Spark, ML, schema on read with caching. And then, here they have their big product, which is the output at the end of the day is real information that's actionable and useful. So they have actionable insights, summaries, visualizations, APIs to access it, and dashboards of this information as well. And then from there, they have a pull model where I suppose they expose an API that clients that they have can pull information. And then they also have a model here where they push this data out. So not sure what kind of data they're pushing out. They have it here, but I would be interested in learning more about exactly what they are pushing. So that's kind of a little bit about this company. So let's kind of read through at least this top section here just to understand like what this whole thing is about. So let's do it together. So 3Victors implemented an AWS cloud-based architecture. Sorry, I just want to get my mouse here. Yeah, cloud-based architecture to capture and durably store over 10 terabytes of daily streamed air shopping data messages. So air shopping. So I guess this is booking information into a data lake. Dozens of ETL jobs. ETL stands for extract, transform, and load. Jobs run at regular intervals to populate use case specific data ponds. By the way, they're using these terms a lot, data ponds and data lake. I'm not too big into the big data world. I had to look these up, so let's just show the definition here really quick. So a data pond are subsets of data lakes that are separated for privacy, governance, technology, or costs. And a data lake, I've heard this term before, but let's just go over the definition. So a data lake is a storage repository that holds a vast amount of raw data in its native format until it is needed. While a hierarchical data warehouse stores data in files or folders, a data lake uses a flat architecture to store data. So essentially, data lake is just a huge swath of raw data, and a data pond is a subset of that data that could be, I suppose, transformed for a specific use case or policy-based separation. So that's what those two terms mean. I would just try and remember that because it's used throughout here. So let's just go through this last part. So simultaneously, the implementation provides an extensible real-time predictive analytics pipeline for demand forecasting and deal classification. So that's interesting. Demand forecasting, just want to underline that. And deal classification. So how I interpret this is when you go to a website like Expedia or something, and you're trying to find like, oh, I want to go to, I don't know, I'm just making something up. I want to go to Mexico. What's the best time of year to go to Mexico? Well, it's probably not like in August or July or August, because that's when kids are off school. So the demand for this period of time will probably be high, and I would expect that this application captures that amount of demand and suggests better times to go that are cheaper. And deal classification, so it would probably look at historical trends of what the price is over time, and if something is below a certain threshold, it can mark it as a good deal, moderately good deal, or a bad deal, or something like that. Okay, so that is kind of an introduction here to what we are dealing with. So let's go through each of these numbers here, and they number it off pretty well. I won't get overwhelmed with this. We're going to go through this one by one or piece by piece. So let's just take a look at number one here. So Amazon Route 53 directs per stream. Let me actually make this a little bit bigger so you can see. There we go. Amazon Route 53 directs per stream vendor content to source-specific AWS Elastic Beanstalk application orchestration at 20,000, wow, 20,000 per second HTTPS post transactions, auto-scaling for, wow, this is a run-on sentence, auto-scaling for peaks and valleys using Amazon EC2 spot instances when possible. Holy moly, it keeps on going. And monitored with Amazon CloudWatch while logging application-specific statistics to an Amazon Redshift columnar data warehouse via Amazon Kinesis Data Firehouse. Oh, I'm out of breath. That was a lot of things. So let's go through each of these one by one and try to understand what's happening here. So they have like an endpoint here that they expose, and it looks like someone or something is posting data to this application, and this is based on Elastic Beanstalk. Now, if you've never used Elastic Beanstalk before, it's a very convenient way to host your application. Comes with features like auto scaling, application load balancers. It sets all your networking up so that everything is good to go. It supports CloudWatch and all that. So it is a very convenient way to get an application up and running very quickly without having to worry about low-level components like EC2 and VPCs and all that kind of stuff. So that looks to be what they are utilizing here. And so they have two clusters, so to speak, that are handling this data. They have alarms that are registered over here to kind of monitor that process to make sure that it's running smoothly. It's always a good idea to have alarms to just monitor your consumption rate. Maybe if it dips below a certain threshold, you fire an alarm. Or if processing stops at any point in time, you also fire an alarm. A whole bunch of different reasons why you would want to have alarms here. Now, why they have two separate ones, not quite sure. Maybe for two different use cases. We can see here there's like two directions that it goes to, one here and one here. It could be the case that like this one is pushing in this direction and this one is pushing in this direction, but they don't really go into that too much. But basically, this is like raw data capture here, where they're just consuming all this data that's coming in. So what do they do with it next? I actually want to go to the right here to just close off number one. So they're putting this data to Kinesis Firehose. So if you've never heard of Kinesis Firehose before, it's a great way to batch your data. So you just write your data to a single endpoint using the Kinesis SDK. And behind the scenes, that data is going to be chunked into batches, and you can set the size of the chunk, whether it be 1 megabyte, 5 megabytes, and whether you want your chunks to last for like 5 minutes worth of data or longer. You can control all that kind of stuff. And the neat thing about using Kinesis here is that there's a way to set it up with S3 so that it automatically populates into a Redshift cluster. So for those of you that have your data somewhere else and you want to get it into Redshift, this is a great way to do it using Kinesis. And then from Kinesis, it goes to S3. Then from S3, it goes to Redshift. They're not showing the S3 part here, but that's kind of how it works. So this is kind of how I interpret this is raw data storage. Sorry, my writing is bad. So this is raw data storage, and they're highlighting it's for reporting purposes. Okay, so this makes sense so far. One thing here, I don't want to do that, but they're using the term KPL here. I just want to note that KPL. That stands for Kinesis producer library, and they're using Kinesis streams in this case, so Kinesis data streams. And if you've never heard about Kinesis data streams before, I guess it's kind of similar to SNS, or SNS and SQS, but with Kinesis data frames or Kinesis data streams rather, you can replay your data from a previous point in time. Your data is stored within the stream, and you can have multiple consumers that are all reading off of the stream concurrently. And the way you do that is through the other half of this equation, which is KCL, which stands for Kinesis Consumer Library or Kinesis Client Library. I can't remember which one. And that's where you see here KCL. Actually, I want to get a different color for number 2. Let's get red. So KCL. Okay, so that's about it for number 1. Pretty straightforward. Let's see what's going on for number 2 here. So captured pricing data is lightly transformed into a common format. So they're normalizing their data at this step. Serialized and placed on a durable 24-hour Kinesis streaming buffer balanced across 100+ shards, supporting checkpoint time range replay for downstream issue remediation. So what that effectively means, like this is a little bit more about what Kinesis does, but you can replay your data from a previous point in time. Say that there's a failure downstream. You're like, oh shoot, we lost all the messages, which sometimes happens with SNS, and then you ask your upstream consumer to replay the messages. With Kinesis, that's just a feature that's built in. So you can say, go back to 6 hours ago, and then it'll replay the messages, and anyone that's consuming that data will reprocess them. So it's a great way for disaster recovery, or a great disaster recovery mechanism. And the fact that they're using all these shards are just like the units of Kinesis. Each shard can support up to 1 megabyte per second, I believe is what the number is. So if you're consuming large amounts of data, you need more than 1 shard, obviously. And I think they said they're supporting 20,000 transactions per second. So they need quite a bit of shards. Also has a concept of partitioning where you can partition your data by different keys, but we're not going to really get into that in this talk here. So then what are they doing with this after it's normalized? So it wasn't clear to me, by the way, if they're normalizing at this step, like here is the normalization, or it's like here they're normalizing, but I'm not 100% sure, but let's just run with this. And it's actually kind of going into number 3 here. So maybe we want to read number 3 here. 2 concurrent pipelines fan out from the streaming buffer. Cost optimized using the 2x read versus write stream. I don't know what that means. Feeding AWS Elastic Beanstalk compute clusters that read and deserialize the data in real time. So they have normalized data coming in this way, and then they're piping that out to 2 different consumers that want to read off of that normalized data. Kind of makes sense. And then from there, they are doing something similar like we saw over here, except that they are storing more formatted data, so normalized data into Redshift, and they're saying it's for reporting. Okay, interesting. And something, so ingest data lake. So this whole process here on the left-hand side is for their data lake, and this whole thing on the right-hand side is probably for it says real-time fan out, but pushing data to their consumers. If you remember when I brought up their architecture here, they had this notion of push, which I classified or talked about over here. So I assume that's what kind of this left-hand side is referring to. I'm just going to draw a line here to separate. So this right-hand side is referring to the push system, and the left-hand side is kind of the data processing and analytics side. But this is just a speculation. Let's just see how this plays out. So on the right, they're doing, I guess, something similar where they're pushing to Firehose again, and that's going into a Redshift again. Not sure, like this is kind of what I was talking about. They don't give you all the details here of why this is necessary, but you just got to take their word for it. And okay, so we're going to 6. I don't want to go, so we're going to go down the left path first. So after they normalize the data and ingest it again, what happens at number 4? So at number 4, a data lake pipeline durably persists in a cost-optimized Amazon S3 intelligent tiering bucket via multi-part upload with directory paths suitable for partitioning and cross-account accessibility. Schema on read data lake mappings are updated in AWS Glue Metastore, supporting Amazon Athena Analytics. Bucket-defined lifecycle policies for archiving to Amazon S3 Glacier Deep Archive optimized cost. Okay, so that's interesting. So what are they, actually, let me get my face out of the way. I'm going to put my face at the top so that I don't kind of get in the way here. Okay, so they have their normalized data now going into S3, and that is being pushed into S3 from their Elastic Beanstalk cluster. And they're doing multi-part upload, probably because these files are really, really big and they need to do multi-part upload. So it goes into S3, and so there's different tiers of S3 depending on your access patterns of that data. And I have a whole video on this, by the way, S3 lifecycle policies. Intelligent tiering basically keeps it such that data that is frequently accessed, or is it more recent data that's uploaded? It's one or the other, if not both. But basically, fresher data is kept in a certain storage classification that makes it faster to read. And data that is kind of not used very often will be put to more cold storage, so that you're not paying the premium for it. And that's what Deep Archive here is with AWS S3 and Glacier. It's data that you want to have around, but you're not going to need it for a long time. And so having Glacier here is a great way to reduce your costs. If you have data that you want to keep for maybe you want to audit it later, but you just don't need it right now, and you want to reduce your cost as low as it can get. So it's like a fraction of the normal cost of using S3. So that's what number 4 does. Let's take a look here. So from there, it goes into this EMR cluster. I suppose maybe this is like a push setup that they have going on over here. So the raw data that is in normalized format is delivered to S3, and then either push or pull occurs on this EMR cluster. So this EMR cluster is now grabbing all this data. And now let's read number 5. What does it do with it? So periodic ETL jobs on customer SLA deposit results into cross-account accessible data ponds using the Amazon EMR transient massively parallel compute framework, cost optimized with spot instance fleets. Schema on read data pond mappings, updated in AWS Glue Metastore, facilitating Amazon Redshift Spectrum access integrated with Amazon. Wow, these sentences are way too long. With Amazon Redshift, whereby customer jobs are run that join and filter ponds into columnar tables for BI tool access. Holy moly, guys. Shorter sentences, please. So from here, they are segmenting it, right, into different ponds. So there could be like different each arrow can represent a different pond, and this could be like for different use cases. So all of this data is going again into multiple different ponds, and it's stored in CSV format. And the same kind of thing happens. So you have the intelligent tiering and Glacier for cold store. And then from there, again, the same kind of system. You can do S3 to Redshift directly, similar to what we saw over here with Kinesis. From Kinesis, it goes to S3 to Redshift. Same kind of setup down here. So you're going from S3 directly to Redshift Spectrum. I can't remember what Spectrum means. Is it the serverless? No, there's no serverless Redshift. Someone let me know in the comments what Redshift Spectrum is. I can't remember. The schema is normalized via AWS Glue, and then they have Athena here for analytics. This is a very, very useful tool. Athena lets you basically do SQL on data that's stored in S3, and you only pay for the data that you scan. So super, super useful stuff. Great for BI and data analytics and all sorts of use cases. Also great for like logging and auditing. I have a video on this to how to set it up. You should check it out. I'll put it in the description. But we can see here that it's used by internal users that are querying Athena and thereby querying the data source here. From there, the data is accessed via Tableau. Tableau is like a dashboarding tool. The AWS equivalent would be something like QuickSight, I believe is the name. And then from there, it's going into Redshift. I don't think they tell us why that's happening, but I suppose some of this is going to remain unknown. But yeah, that's kind of it for the left-hand side here. Not sure what this engine thing does. I guess they have some custom proprietary stuff that they don't want to share. Okay, so that's it for the left-hand side, which was the data analytics and all that. Now let's move on to the right-hand side. So we stopped at 6. That was actually the last one. So what does this thing do? So a real-time analytics pipeline fans out to unlimited Kinesis stream buffers that support an extensible micro-batching framework. A default use case populates Amazon Aurora, which is RDS, by the way, and Amazon Neptune, which is a graph database, for customer API access via serverless Amazon API Gateway and AWS Lambda. Database I/O is optimized using Elastic Cache. Okay, cool. So there's a lot of stuff going on here. So Normalized data is going into KCL again, and I mean, don't know why they're doing this way. Actually, this makes sense. So they're producing, and it's going into a Kinesis stream, and then they're reading off of it here. And I suppose they have the same setup going on over here. I don't know why they need two different Kinesis streams here, and then one being read here, and then one being read on this guy. But I guess that is something specific to their application that we're never going to know. And then that's being read off of Elastic Beanstalk. Again, wow, they're using Redshift a lot here for reporting. They must do some kind of transformation. They're noting here that it's summarizer. So probably aggregates for time windows or airplane airports rather. And so it kind of gives more information at an aggregate level. And then from there, they do this micro batching and insert it into Amazon Aurora and Neptune. So Aurora that allows you to do some great relational style queries. And obviously this matters if you have multiple different tables that are linked via keys. And Neptune is a graph database. And I've actually used this before. It's a very, very fascinating technology. So it's great for like airplane type use cases are perfect where you have nodes and edges that connect the other nodes. And if you imagine like the world's airplane network, all the nodes are airports and all the edges are paths between different airports. And to go from point A to point B, it's not always going a straight line. You may have to go through a different node. So maybe you go A to C to B instead of going directly to B. Maybe that's a shorter route. And often you see that when you're trying to buy an airplane ticket, it's like there's like two stops, but it could be faster than... Actually, I guess two stops are never faster than a direct, but oftentimes there's more than one way to get to a destination based on the edges in the graph. So I assume based on the fact that they're using this technology that they have these kinds of queries that are like, how do I get from here to here with a stop here? You can use Amazon Neptune to kind of traverse a path between these nodes and edges to find the most optimal route. So that's supposedly how they're using this. And Aurora for just relational style queries. And what's interesting here is that, so they have a API model where they have an API through Amazon API Gateway that's served by a Lambda. And then they have a cache here. And I suppose the reason that they have the cache is they're doing some bulky queries on Neptune and on Aurora. And so this Lambda probably does the query and then caches the result. So the next time that a request comes in, it just looks in the cache and it's already there. And this is useful because Neptune has two types of queries, OLTP and OLAP. I can't remember which one is which, but one of them is for when you want to do like discovery style queries. So like, how do I get from this node to this node? And internally, the database will traverse all the edges to figure out, okay, what's the path? It'll tell you the result. As you imagine, that's a very expensive operation, much more expensive than something like give me a row that has this ID in a database. So it becomes very useful to have this Elastic Cache layer that helps optimize and take some stress off your databases. So that's what they are doing here. So unfortunately, there wasn't too much about how the application is actually used from like a consumer perspective or a customer perspective. But this kind of gives you an idea of how these applications are built. Let me know if you like this style of video and you enjoyed this, if it was useful in any way. I'm happy to make other videos on these architectures to give you a better idea of how AWS works in real life. But yeah, if you like this, please don't forget to like and subscribe, and I'll see you next time.